Okay, so I did. And then she just kind of fumbled.
All right, is everyone here? Everyone's here, okay. I'm not sure how to share my screen. Sorry, I'm on my phone right now. My computer, it's like not right now. So I'm trying to see how to share my screen. Okay, here it is. Right. And start broadcast. All right, can you guys see my screen? And if you guys want, I don't know how it usually works for BBMC, but you guys can just unmute and just say something when you guys like have a question or something going on or anything. Feel free. Someone in chat, tell me if my screen is being shared right now. Then I'm good to go. Being shared? Okay, great. Okay, so welcome guys. This is the I guess like a practice session just for me to kind of get to know you guys, for me to demonstrate my teaching skills on USACO. I hopefully will be a gold instructor in the following year, so that'll be cool. First things first, I guess as like an intro, my name is James. I'm a incoming freshman at MIT. Right now I live in Boise, Idaho. It's in the Northwest area, so pretty far from Maryland. Yeah. In high school, I did USACO. I made it to platinum in grade, and then this USACO now. I did try to make it to camp, but that didn't work out. Yeah, that's from me. I will go ahead and start the presentation that I made on the over. I'm not sure why. So let me know if you guys have any questions, concerns, or technical issues. Just unmute. So problem one is visits. Basically, we have n cows in different positions. N can be up to 100,000. And each cow wants to visit a buddy cow AI. And this is exactly one buddy cow. Now, each cow in some arbitrary order will want to visit cow AI once. And then they do this attemptation by through the following process. If cow AI is already visiting someone, then they just stay put and they don't visit them. If cow AI is available and they haven't visited somebody, then cow I will visit them and then generate VI points, which is determined by I. So, and because it's arbitrary, you can do it over any permutation. So like cow 3 can go first, then cow 1, then cow 2, or then cow 2 can go first, then cow 1, then cow 3. And basically, you want to determine some kind of visiting order such that we can get the maximum points, the maximum total points generated from these visitations. Okay. So the sample input, let's just go over it. We have 4 cows. Cow 1 wants to visit cow 2, and if they do, they generate 10 points. Cow 2 wants to visit cow 3, and they generate 20 points. Cow 3 to cow 4, they will generate 30 points. Like cow 4 to cow 1, if the visit happens, they will generate 40 points. So we have this configuration, and we want to find some kind of order in which to visit each other to find the maximum number of points. So we could try this permutation 1, 4, 3, 2. So cow 1 visits cow 2, and then they generate 10 points. And then cow 4 will try to visit cow 1, but because cow 1 is already visiting cow 2, you don't generate the 40 points. Then cow 3 visits cow 4, he generates 30 points. And then cow 2 cannot visit cow 3 since 3 is already visiting. So in total, we have 40 points that we generate from this permutation or this arrangement of cows. Okay, so now we'll try a better permutation because that one, it obviously wasn't that, like the most optimal because we had 2 cows that couldn't visit their respective AIs. So let's try permutation 2, 3, 4, 1. So cow 2 would try to visit cow 3, and then they will get 20 points. 3 visits 4, they'll get 30 points. 4 visits 1, they'll get 40 points. The 1 cannot visit 2 since 2 already visited. So they're the only that does not generate points. So in total, we get 90 points. And this, qualitatively, this seems like the best orientation, right? Because we only drop 1 cow. Only 1 cow isn't able to visit, and that cow is cow 1, which has the smallest number of points that they generate. Basically, in some hypothetical world, maybe we could have gotten 100 points, and we got 90 points in this world by sacrificing cow 1, which seems optimal and is the correct solution to this sample case. If anyone has any questions, just feel free to I think typing in chat. Just unmute, please. Thank you. All right, so we have the sample case, and we want to figure out how to solve this for say any arbitrary configuration of cows. And I guess the first thing that we can notice is that separate kind of components of cows that are connected to each other, they won't affect other components. Meaning that, like, say we have these 2 components, left component, right component. The point generation of cows in the right component is independently determined of the cows in the left component. And what this means is that we can basically find these components and solve the problem individually on each component independently of each other. Where independent basically means that like it just does they don't depend on each other. Now in the sample case, just going back to specifics, we did have to sacrifice a cow. And so why is that? You know, why can't we just have all the cows in each other? Why is that not possible? And just let you think on that for a second. Now the answer is that I guess for all simple cycles, we kind of have to sacrifice a cow, right? Because like one, like if cow one visits cow two, then that's like one less cow that can be used in the entire system. And then once we're at the last cow, it's guaranteed to have no one else to visit. So one kind of thought that we can generate is that like, okay, so for every simple cycle, since this sample case is a simple cycle, right? For every simple cycle, we have to sacrifice exactly one cow. Through the aforementioned process, we don't have to sacrifice two more cows. We only have to sacrifice one. And optimally, we can choose to which cow we want to sacrifice, right? If we start, because we started at cow two in our question, right? That meant that you can choose which edge to sacrifice. You can sacrifice edge 10, edge 20, edge 30, because we want the maximum number of points that we can get. We obviously sacrifice the lowest weight edge. So in this case, the edge one from cow 1 to cow 2. Right. So we have that. So we kind of have that theorem, right? Basically, for a given simple cycle, just from this test case alone, we know that we will sacrifice exactly one cow only, and we choose the lowest weight from that. And we can generalize even further. In fact, we can even say that each connected component only has exactly one simple cycle. Just take a minute to think about that. Why is that a thing? Why can't I have multiple simple cycles? Now the reason is because the out degree of every node is equal, which means that if we were to have multiple simple cycles, the connected component, some nodes would have to have out degrees of more than one. And then we also can't have like regular cycles that aren't simple, because that would also require nodes that have an out degree of more than one. And just for reference, these type of graphs where the out degrees of all of these nodes are one are graphs. So they're pretty cool. I'm sure there's a new page on them where you can learn more about the properties. Yeah, pretty cool. And so basically, we went from the sample case. We saw that we had to sacrifice at least one cow. We generalized so that all simple cycles, you have to sacrifice one cow. And now we generalize even further. We showed that every connected component exactly has exactly one simple cycle. In that simple cycle, we sacrifice exactly one cow. And that one cow we determined to be the cow with the minimum weight. So it took these two steps of reasoning to get to our solution. So we can construct an algorithm, right? You know it's good to think of it think of our solution as like taking away minimums. So what we can initial score with the sum of all the values in the system, and then we take out weights from this initial score to determine the final score. That's the maximum. Basically, so we start with the score, and then we loop over all the classified the connected components. And then within each connected component, you'll find the simple cycle within the connected component. And then within that cycle, we will find the minimum weight in that cycle, and then we will subtract that weight from our total score. That is a very high level overview of our code. Now, this implementation is a bit different. I guess the main thing to note is that to define simple cycles, we use what's called Boyd's algorithm. Boyd's algorithm is also known as the hare and the tortoise algorithm. So basically, we start at some random node. We have this two pointer approach where we have one pointer that's slow and one pointer that's fast. What that means is that in a given iteration, one pointer will jump one node and the other pointer will jump two nodes. And then when the pointers finally meet each other, when they finally like converge to the same node, you know that the path that they took is a simple cycle. That's the essence of Boyd's algorithm. And now, once we're in that cycle, we can basically iterate inside that cycle to find the minimum weight and subtract that from our final score. Does anyone have any questions about what we just went through? It was a bit fast. Maybe about like the implementation or about like the intuition or anything. All right, sounds good. We can go on. And I guess to recap, the main thing to take away from that problem is I guess this idea of like generality, I guess. How do we get this application to the final solution using these steps? All right, problem 2 is subset equality. So let's look at this. So we have Bessie, she sends two encrypted strings S and T. S and T, the length of them are less than or equal to 100,000. And then John, he wants to like make sense of it using Q queries, where Q is less than or equal to 100,000 also. Now, in a query, each query will have a certain subset of the alphabet. So it could be like, if the query is ABD, it means that the subset, you would only use that as ABD in the alphabet. And then for each query, you want to see if the two strings are equivalent when restricted to the set of letters in the query. And then if it is, we put yes. If it isn't, we put a no. So let's do a simple input. So we have S and T. S is AABCD, and then T is CAABD. And then let's go through the queries. I would say that the sample process. So query 1 will be A. Now in both cases, they both have two A's, which means that they're equivalent. And we output a yes for those queries. It's pretty simple. Query 2, we have an AC. And so S would reduce to AAC because we basically remove B and D because they're not in the query. And then T would reduce to CAA. Now, the S and T are not equal, so we would output a no. Whereas A2. And I guess to go even deeper, like to see if two strings are equal, you just compare like whether each character at their respective index. Query 3 is ABD. So basically, we would just remove the C from both strings. So S would be AABD, T would be AABD. Now both are equivalent, so we would output a yes for query 3. And query 4, the entire alphabet. Now we know that these two are not equal just by comparing like the first indices. So we would output a no. So we have the problem. We can construct like a brute force solution initially. Basically, for every query, we would just like construct the respective strings on the subset of this query and directly evaluate each string. Now this would take for every query, since you have to at least do operations on the entire string. And then with Q queries, this would be a 10 to the 10th power. We have about 10 to the 10th power operations, which is a bit too much, 10 billion. We want to be in the 200 billion-ish range. 200 billion is good. Now, USACO does have a subset, does have a subcase for Q and N being less than 1,000. So you can get one test case using the solution. You get a 20%. So you want to do better than that. We basically want to find out how do we make this a more efficient process, right? Because obviously directly comparing every single indice for every single string Q times is not efficient. How do we make it more efficient? That is, if it were easy, easy for itself would be so much easier. Okay, so I guess we can just notice one thing, right? C is in a different position than the two strings, obviously. Now, it's not like a concrete thing, but we can kind of notice that, like, okay, C is in like a way position. It's obviously not a good direction in most cases, right? Because C kind of like jumps over the A's and B's. So qualitatively, C is it's just a bad letter, right? And that, so how do we kind of jump from this reason to a quantitative algorithm? In addition, we can notice that like A and C will fail, B and C will fail, and so C and D will go C and D succeeds. So it's like we have this letter that fails most of the time. How do we determine when it fails like exactly like which position it fail? That's the question. I'll just let you sit on that for a while. And again, if you have anything, if you want to talk about anything, how do we use this reasoning to construct our algorithm? All right, so let's just think about it a bit more. Let's use the query ABC. Now ABC, for S, it will be A, B, C, and for T, it would be C, A, B. So the ABC query will fail. But we can also infer that also without having to directly compare. Now, why is that? Well, we know that AC, we know that query AC fails, right? AAC, CAA are different strings. But because AC fails, then adding like an additional restriction onto it doesn't help us space, right? It's not gonna like magically become a good query when you add more and more restrictions. Right? Like intuitively, adding more restrictions of letters, it's like shaving the edges of snow to make it a snowball, right? It's not gonna add more snow. It's gonna make the solution more. Right? So because AC fails, we can like infer that like APC fails, and it's just because strings S and T are inherently different when both A and C are present. So for any query, if it contains both A and C, we know it's gonna fail just because it has restrictions, even more restrictions on a bad solution, which is just not good, right? It's just not good for the query. So that's the key observation that we have to make. Now we can generalize this from query to algorithm, where we can say that for any two pair of letters, L1 and L2, if the pair fails, then any query containing both letters will also fail. That's the final observation that we have to make. And it's powerful enough that we can use this to create a solution that runs faster than human time. Let's look at the code for a second. Or never mind. Let's not look at the code. So our algorithm, this is a pseudocode. Our algorithm is basically we do some pre-computation over the and then we use that pre-computed memory to solve the query problem fast. So over all pairs of letters in the alphabet, we determine if S and T are equal in this pair. And then we can save this result to memory. So we can store it in like a 2D array, right? And we save it to be yes or 1 if it's true, if it's equal, or 0 if it's not. And then this will take O of n time for every pair of letters in the alphabet. And there are 13 times 25 pairs of letters in the alphabet. So that's like not that much. It's like 300 per 100-ish. It's enough. It results in about like 3 million, 4 million operation, I think. So it's plenty. This is a pretty fast algorithm. And then for each query, what we want to do is we want to loop over each pair of letters in the query first. And then if any pair fails, or if any pair in the 2D cache has a 0, then the query itself fails, right? Because if any two pairs fail, then the entire query with multiple restrictions on it. Now, if every pair succeeds, then every pair succeeds, and the entire query will succeed. Now, this it basically loops over every query, and within each query, it loops over every pair of letters. So it's the same time complexity. In total, we will have about 65 million operations which is pretty good. Assuming that A equals 26, the number of letters in the alphabet. Now, there is one edge case that we have to consider. Like when the query only has one letter, we can't really loop over all pairs for our algorithm. That might seem like a problem, but you can just compute this case separately, right? Because if you only have one letter, then all you have to do is just count how many times that letter appears in the strings S and T, right? And then if it has the same frequency in both strings, then that letter is yes. Otherwise, no. And you would want to do this in frequency. Right, that's our algorithm. Let's look at the code. This goes in Java. It's a bit hard to read on the phone. I will zoom in. So as you can see here, we will this first step is the edge case. If the queries only have one letter, so the freaks S and the freaks T arrays, they will take care of that. And then we build this 2D cache, this compatible 2D Boolean array, where we build all pairs of letters, and then we will construct the string builder for letters S and T, and then basically build S and T from only these two letters, and then we just see if they're equal to each other. If they are, it's a 1. If they aren't, it's a 0. And then so that's a pre-computation, and then we go to the queries, where for each query, we yeah. Yep. So this first part, it's a weird way of checking the first edge case. It's equivalent to this entire first section, starting from S sum T sum and ending at if S equals is not equal to T sum. That first section is equivalent to saying if the query is one letter, and then check the frequencies of that letter in S and T. Now the second part is the where we just look over all pairs of letters inside the query alphabet, and we just see if any of them are incompatible. If any of them are incompatible, we will return a no. Otherwise, we keep the answer as a yes, and then we finally append this answer, this query answer, to our final answer, and submit that to our Anybody have any questions? What we just went through? The main thing to take away from this problem is to utilize the fact that we don't have many letters in the alphabet compared to n. N is like 100,000. We only have 26 letters in the alphabet, so we can afford to have an algorithm that runs like in square time of the number of letters in the alphabet. If that shaves off even like a factor of n, which it does. In our algorithm. Basically, yeah, that's the main takeaway. If we had like 100,000 letters in our alphabet, we'd have to do something else. But generally in Silver and Gold, there will be these kind of exploits that you can find. Or see that this part is like very small. I can construct an algorithm that is very small regarding this variable, but saves on time, kind of that's the main takeaway. And the other key observation is is kind of this observation that like adding more restrictions on an already filled case, it makes it feel that's one thing to kind of exploit in the structure of the problem. So that's what USACO really is, right? Just finding ways to exploit the structure. Using problems on these nodes. All right, let me check if there's any questions. No question. I also wasn't streaming the video. Yes, you guys can see me. All right, sounds good. All right, if there's no questions, we can move on. Probably three cal operations. So best has some string that contains only the letters C, O, and W. So that's a note, right? Only 3 letters. And the length of the string is less than or equal to 200,000. Right. And we want to convert this string into a single C using only 2 operations. We can either delete adjacent equal letters, so COO, we remove the 2 O's to make it a C. And or we can choose any letter and replace it with 2 other letters in either order. So we can take a C, the other 2 letters besides C are O and W, so we can make it into an OW or a WO. So we have these 2 operations, right? And we want to see if we can convert some arbitrary S into a single string Q times. What to do is use for Q strings. Each is, we have less than 200,000 queries of varying substrings. Never mind, I read this wrong. What to do is we have to see if this is possible for Q queries of varying substrings on S. Yeah, I was gonna say since that's a bit impossible to have data and input. So we want to see if this is possible for Q queries of varying substrings. It'll give you like 2 indices, a start and an end indice. Basically, and that determines what substring you want to evaluate. Sorry if this is a bit scuffed right now. I'm outside right now. My computer, it's like messed up right now. I think I broke it. It will be working next time. So don't worry. This is just a one time. So let's take a sample input. S is equal to count. The string count. So the first query is from 1 to 1. Now 1 to 1, S will be C. And since it's an AC, we return a yes. Now LR is equal to 1, 2. Okay, so S starts as CO. And we can do a ton of operations operations on it. We can like convert CO to C, CW to W to CO again, CWC. But we're gonna find that like no matter what we do, we can't convert to C. We will show that later, but the sample says you can't do it. We will assume that you just can't do it, right? And it just looks like it looks very hard to essentially see. Now LR equals 3, so it's the whole string. And again, we try to convert this. We can convert this to CC, which is very close, but you can't remove only C. You'd have to remove both C's, right? In a removal equation. So you can't do that. And again, it's just impossible to convert this to a single C. Okay. And then final query is LR equals 2, 3. So S is equal to OW. And we can do that. We can convert this, right? Because we convert OW into C by yeah. We can convert O to like we can convert O to like CW, and then we'll have a CWW, and then we can remove the operation using an C. So we can do this. So we have the sample input. Yeah. Now it's time to think about the problem. Actually, no, I'm not going to show this. I just want you to think about how you can solve this. What things can you notice about the structure of the problem that would allow you to solve this? Now, one obvious one is that like, oh, there's only 3 keys, but how would that help you? Now, because one heuristic that we can apply to the situation is that we after testing it out, I'm sure you guys have already done it on your own. Is that we can usually convert each string, any string, regardless, into a single character. Now, how do we do this? Well, we can do like a constructive algorithm. We start with the first 2 letters. If they're different, we replace it with the other respective. So if it's CW, we replace it with an O. Now with the first 2 letters, if they're the same, we delete them. And we can apply these operations again and again and again until we have a single letter, right? Since they only take in 2 letters as a parameter. Once the only time that they don't have 2 letters is when there's 1 letter. So it means that no matter what, we can have 1 letter at the end. Now, if we're lucky, this might be a C. And then if we're always lucky, then we solve the problem, right? But we're not always lucky. Sometimes it's a W. Sometimes it's an O. But is it possible to get from a W to a C or an O to a C? That's the next notice, is that we hypothesize that we cannot go from a W to an O, W to a C or an O to a C. I just want you to think about it. It's like why can we not do that? Why is that not a thing? Now in the sample case, in the sample case, we have this right here, right? We convert this to a single W. So maybe we can convert it to a C, but the sample itself says that we cannot. Why can we not go from one single letter to any other single letter? Why is that a thing? The big question. How do we make this observation more rigorous? And anyone wants to type in chat, feel free. I'll type in chat. So just to get you guys can type it. Okay. Oops. Oh, it's like, why can we not go to C? C, W, Y. We can bring in some math. So I guess it's okay. So I guess one thing to say, in a contest, you can actually just test out this heuristic, right? You can try just like seeing if something decomposes into one letter through some algorithm that's faster than just manually doing it, and then see if that and then basically return yes if it's a C or return a no if it's a W or an O. In contests, you can do that, and it would work. But because we're here to learn, we want to show why that's not possible. And in the process of showing why that's not possible, we actually find a solution that's, I believe, a lot faster and a lot more elegant than the pseudo brute force algorithm that you would do in contests. We noticed that pairwise parity is preserved with each operation. Now, what does that mean? Pairwise parity is basically the parity of the sum of two elements in COW. So C plus O, O plus W, and C plus W. The parity of those three combinations is preserved. Now why is that? So we can test out the two operations. So let the lowercase c, lowercase o, and lowercase w denote like the frequencies of each letter in the string. To get like the running count of how many letters of those COWs is in the string. Now in a replace operation, we take away one letter and then add to the other two letters. So COW is C minus 1, O plus 1, and W plus 1. If we replace the C with an O and W. Now in this operation, you notice that C plus O is still C plus O, right? So if it's the same value, the parity is the same. Same thing with C plus W. And O plus W, what happens is that their sum is O plus W plus 2, which means that the parity is the same. If O plus W is even, O plus W plus 2 is also even, right? And this is true if we replace any letter with the other two letters. Now in our remove operation, this is also it also preserves parity with like the single letter itself, because we just remove 2 from any given letter. It stays even, it's even, it stays even, it's odd, it stays odd. Right. That's the that's the preservation of parity. So like the remove operation preserves single letter parity. Second letter preserves pairwise parity. So in total, pairwise parity is preserved with every remove and replace operation. In contests, you would probably not do this. but it is good to learn. It is good to intuit if this ever comes up, if this concept ever comes up again. Now we can see how this affects like ending states, right? So if you have a single state C, it corresponds to state 1, 0, 0. And ending state W corresponds to 0, 0, 1. Now you can notice that they have different pairwise parity. That's the main thing. It's that C plus O is 1 for ending state C, but C plus O for ending state W is 0. And you can say that for every pairwise parity. Now, this is pretty big because we know that because they have different pairwise parities, that means that you can't go from one to the other, right? Because the operations keep pairwise parities like the same, it means that like because C and W and then we can infer O have different pairwise parities, it means that no matter what operation we do, we can't go to them. It's mathematically impossible to go from them just because they have different pairwise parities, and that's the cool thing with this preservation property. So how does this observation lend itself to the final solution, right? How do we use this? How do we use this in our algorithm? So in our algorithm, we can just count the number of C's and W's in the substring, and then we can just compute the pairwise parities itself. And then how do we to go from these pairwise parities to state C? We basically see if C plus O is odd and O plus W is even, then it corresponds to C like no matter what. We can basically compress the entire string into a C using the aforementioned like process. And I didn't explicitly write and say O, but I guarantee O does not have the same pairwise parity as C and W. And the property that C plus O is odd and O plus W is even is unique to NSAC. Now, obviously, there is like an implementation step that we have to be careful on, because obviously, if we directly count the number of C's, O's, and W's every time, that's an Q times N solution, which is too slow. We use prefix sums to compute that process. So we have here our main method. We compute the prefix sums in the beginning, right here. And then for every query, we literally just see, we just find how many C's are used for the substring. Now, if query counts 1 and query counts 1 corresponds to O, plus query counts 2, which corresponds to W, if that's even, and C plus O is odd, then we return a yes, otherwise we return another. And we just do that over every single query. This is a O Q plus N solution very fast. So it's plenty enough operations to find the final answer. During time, I'm gonna be a bit but I assume this is like a 1 hour thing. It's a simple competition, but I can go with go for the order. All right. Now here's a cool alternative solution that somebody came up with. It's that we can represent the letters C, O, W as 1, 2, and 3. And then we can represent the empty string as 0. With some properties of XOR, we can actually do both operations. We can combine both operations into one operation. Now, XOR, I'm not sure. I'm pretty sure it's not in the USACO curriculum. I'm sure you guys have learned it in CS classes. You guys have taken CS classes. And basically, it just takes in XOR is an operation that takes in 2 bits and it returns XOR. So basically, if the bits are the same, it returns false. And if the bits are different, it returns true. Now, it's not intuitive, the application of this operation to our, but look here. Let's try an OW to okay, this is backwards. A C to an OW operation, right? We know that 1 is equal to 2 XOR 3. It's also equal to 3 XOR 2. O to WC, 2 is equal to 3 XOR 1. And this is all being done on the binary representation of C, O, and W. The C is equal to 0, 1, O is equal to 1, 0, and W is equal to 1, 1. And it just happens to be that we have two bits, which are the 2 bits used in the XOR operation. And CC becomes the root. And why is that? Well, if you XOR a number with itself, the corresponding bits of the number, they're all equal to each other. Which means that it's guaranteed that the number XOR itself is equal to 0. Which means that for CC, O, and WW, they will all be equal to 0. That's of them. Now, this is very cool. What it means is that like we can kind of encode both operations into one XOR operation. And we can reformulate this problem where basically if the XOR sum of a subarray is equal to 1, if it corresponds to C, then it succeeds, otherwise it doesn't. And that is pretty elegant. It's a very elegant solution that I honestly wouldn't have came up with, but it is a good utilization of the properties of XOR. Now, it's not to say that like this is like some like random like genius solution. It's just that I would say this. It just utilizes the. It's very hard to explain in USACO terms. I guess it's not like lucky that it sort of happens to have the XOR happens to be the godlike operation that we comes to save the day. It's more so this problem having the same structures as the XOR operation that it just happens to be useful in this case. So the XOR solution I'd say it's a bit simpler. Not really. It's pretty similar to our above solution where we just compute the XOR of the string itself, mapping C to 1, O to 2, and W to 3, and obviously mapping the string to 0. But that doesn't really matter in implementation. And then for every query, you just take the XOR subarray for each query. If it's equal to 1, return yes. Otherwise you return no. And we can do this. It might not seem intuitive that we can do this on XOR because like it's a, I don't know. I guess like you might be thinking like we can do prefix sums. Why can't we necessarily do it for XOR? Like, isn't it just like a different operation? And this does have, I think, some ties to like, I think it's because they're it's like a community, both operations are commutative or associated. I think associated. It's because both operations are associated. And for any associated, let me double check. I'm not sure. It's not. I don't see them do use of yeah, it's because they're both associated, and you can perform prefix sums on any associative operation, right? As long as it satisfies the a parentheses a times b parentheses times c is equal to a times parentheses b times c parentheses. It just means that you can basically do the operation on entire subarrays, and it will be the same answer. Whether it be XOR, whether it be sums, whether it even be matrices. I'm sure you can apply matrices since they're associated to prefix sums. Any associative operation, and you can even make your own associative operation. Any associative operation works with prefix sums, and that is something to know. I guess that's like some intuition why like you can even use XOR prefix sums. Right, those are the 3 problems. We're good on time. I guess one thing that we can go over is the time complexity of problem 1, because I believe I skipped over that. The time complexity, what is it? It is, I believe it's amortized over, just straight up. The DFS is open and it doesn't do anything outside of that. Yeah, it's open. Any questions, comments, concerns about USACO, about anything, about, I don't know, life, about math? Feel free to type in anything.
If you want to take care of all this, I can't do it.
Right. Let's see if there's anything else that I not. Yeah, typing about that. We have to go to go over something that you'd like to go over. Okay. I think we went over everything. I guess I can talk about like this entire problem set itself. This entire problem set, I believe the cutoff was 800 for this. So you just put the team itself deemed it very easy, and it's pretty easy to see why. Because in general, USACO problems in this medium level have they have two properties. It's the implementability and the intuition needed, right? If it's hard to implement, it's going to be harder. And if it's hard to intuit like a smart solution, it'll also be harder. Now, before it used to be just like pure implementation, right? And then now they're adding an aspect of like intuition, like a problem-solving skills that you have to know. Like the steps of like generalizing from like certain observations, that's the skill that you need for USACO at this level. And as you can see here, the implementation, like the hard part is the integration. The implementation is very, very like, trivial. Like I'm sure any of you in this could implement these solutions like once you know what to do. And I guess that's why they deemed it easy, because in general, if it's hard, it's going to be both hard to implement and hard to integrate. And that's just a property of how USACO is going. It is getting more difficult as time goes on, and that's just how it is. Yeah, it's not enough just to know certain data structures or know certain algorithms. You have to know how to apply them in certain scenarios using and how to like adapt into certain scenarios. That's the reason why USACO is getting so hard recently. Okay. Well, I think I don't have anything else. I think that might be it. Feel free to reach out. This is my email is right here, jamesll@mit.edu. I can put my phone number here as well. Text me whenever. That's my phone number. And then you can follow me on Instagram if you want. That's my IG. That's with me. Hope you liked it. Would appreciate some advice on what to do. This is my first time doing an online lecture with BBMC. So any advice is appreciated. And other than that, hope you have a good day. Hope you have a good time studying USACO. And that is it for me. Have a nice day.